So you have already seen before a picture of the data acquisition system. So we actually brought a complete replica, sort of, a small miniature version of the SCLS DAX system with us. Is this black box. It's a bit bigger than a laptop, but it also can do a lot more. This is a detector, the 140K CS pad. In order to operate it here and show something, one uses very long integration times, 8 milliseconds. And that means that for 8 milliseconds, it will collect lots of leakage current. And therefore, we have to cool it. And in order to cool it, we use a combination of a Peltier cooler with water. And then in order to prevent condensation, we need nitrogen and purge it. At SCLS, we usually shutter it not with 8 milliseconds, but with 40 microseconds. And therefore, you can basically operate it at room temperature. Nevertheless, it's very rare that one can do characterizations of detectors at free electron lasers. So already just for characterization, we always have to make this effort. And as we have seen, the response, for instance, on the linearity, the problem which we seen at MEC shows only up at the free electron laser. It does not show up at a synchrotron, where the photon come one after the other. Okay, so the data acquisition system, we've seen one picture. So this one is the main screen, the data acquisition control. We can make a shutdown. Basically, usually you don't operate that. The point of contact or the beamline scientists are doing it, nevertheless. You can select your machines. So the big box has more than one computer. One of the machines is making the timing. And one is taking the data of the CS pad. And then one is doing all what we have here as display. At CXI, where they have much bigger detectors, and two of them, how many DAC machines we now have there? 12. Okay, so that's why this is the miniature version. So then it basically works. You select your machines which you want to read out. There is a configuration pane, as we also have already seen, which configures all the settings for a detector, which basically are just placed into. And depending on your experiment, one can decide to operate it in one way or the other. Then you get here this window. So green is good, ready means good, and no damage is also great. Damage is a nasty name for what happens when there is a communication hiccup between the data acquisition system. As the SCLS DAX system is collecting data from many positions, not only from one detector. You also get all the beam data from the electron beam and from the photon beam and from other detectors. And then the computers have to put this all into an event so that one pulse, one shot of SCLS is called an event. And when somewhere in this deepness of this system there is a communication problem and one frame did not arrive in time or it got the wrong number, then the system will show it up as a damaged event. Usually, one doesn't care. I mean, it happens from time to time. It just boop, boop, and then it goes onwards. Here is the event counter and the duration counter. So now, when we go and make begin running, it basically starts running. As we can see here, the events are counting. We are running at 120 hertz. We get no damaged events. That's great. And we are currently doing a couple megabytes per second because it's a small detector. So this is now the image of the detector without any dark correction. So one can see certain inhomogeneity of the dark among the detector. Let me get one of these. So this one is currently my temperature. It's around 1.7 degrees. And I will take this window here so that I have it in view. Okay. Let's cut this one out. Not so easy. Okay, so we make a darker. So in order to make a dark, I will record a run. So we make end running and then again begin running. That's the usual way how it does one here. We make something like 500 frames, end running. Okay, got a bit more. So now I have 620 frames in a dark run, which has the number 76. And Philip is running then a script which takes the data which we collected and calculates the dark, finds all the bad, nasty pixels and puts them into another file so that we can mask them, and also tells us what is the noise of each pixel. And it should be done. Okay, let's see. So then we can basically enable that. And the dark itself, well, the dark itself looks just like the one I've shown you before. I mean, is an exact copy of that, so that when we now subtract this, that's a fix. Okay. So that when we now subtract that, we basically get a homogeneous image which has, I can take these ones here and look at pixels. So I just click here and there, and then we see that it's now jumping around 0. That's nice. Yeah, I can click on this one which says retrain pedestal, and then basically it disables the subtraction of the dark frame. So then one can again zoom out and see this is how the dark frame looks like. So that got now stored, subtracted. Okay. So we enable again this correction. Jump in. Okay. So then the next step would be, for instance, to look at an energy histogram. Let's take the range. Okay. I have channel A. That sounds fine. Plot, close. Okay. So, and now all my pixels are basically around 0. Let's zoom in. Minus 25. Yeah. So this is now the histogram of all the 140 kilopixels on a shot-by-shot basis. So they are now all centered around 0, but because they have a noise, sometimes one pixel is positive, sometimes one pixel is negative. And you see that it shifts around a little bit. It's not always around center. Sometimes the whole distribution gets moved a little bit. That is what is called frame common mode noise. That's actually very often happens in many imaging detectors, also CCDs. And one way, so we can now take this one and, for instance, tell it to average on this spectrum. Okay, close. Okay. And so now the red one is an average of 1 second of 120 frames of the blue one. So we can actually also increase here the frame rate. So it's still collecting and computing on 120 hertz spaces, taking all the data. So the red curve consists of all the 120 frames of the last second. And the blue one, I'm now showing 5 frames per second in the imaging. So we can now enable the correct common mode. And then you will see that the blue line is going to get stabilized. Which also means that now the red line, which is the average, is going a bit less. And it really depends on your setup. If you have pumps, lasers, high voltage injectors, power supplies, grounding, long cables, if you have more or less common mode noise. It can be in some setups, not a lot, it can be a bit more. But yeah, that's sort of typical. I mean, it's not the best setup running it on a desk. I can actually tell, so we can make peak RMS. Noise peak RMS versus time. Channel B, plot, close. Okay, and so now it tells me the width of this peak in RMS is around 5 ADUs. And when we disable the correct common mode, then the red one is getting a bit wider because we are now jumping around. And then it's 5.8, maybe 6 RMS. Okay, so I'm kicking this one back in. We have this histogram, we have this noise. So what we can now look at, bad pixels. Okay, so now let's, so this histogram looks nice, but let's look at a smaller scale, like here. So now I'm zoomed in into the distribution, and you see that there are a couple of guys here. And these are sort of bad pixels. These are noisy pixels. These are pixels which show up in my histogram from time to time. They only show up with one. So usually it's one of them at this amplitude, and that's a total of 15 pixels, something like that. But in the averaged one, I can even go into a logarithmic display. I have 100 frames averaged. So now we have a logarithmic display, and I see that they sort of give me a limit. It's not really nice. And so one of the ways of handling that is that we say suppressing bad pixels. And the script of Philip was taking these 15 pixels, so found them, marked them as being bad, and now they are no longer there. This one, now you say, what was that? A MIP. That is a cosmic. The detector is basically has now no dead time anymore. We operate it in a continuous readout mode. And so from time to time, we get a cosmic ray which goes through the detector. And it's very rare that you see it in the blue, but as said, the red one is averaging all data. There's not one frame missed. And so then we see basically MIP data. So I can show you MIPs. That's very nice. I like this. Yeah, channel up. Okay. Up. So what I did now is I took a hit finder and I told the guy to show me only things which have more than 50 ADUs. Here was one. And when we wait a bit, we will see more. So with the hit finder, we can basically make out of the integrating detector a photon counter. We give it a threshold, and then we say, OK, show me only the ones which are above this threshold. But I have more features. I can not only do digital thresholding, I can also say, when it's above the threshold, then take the analog value and then sum over that. So I'm not losing really my linearity capability. So I can also detect multiple photons, 1, 2, 3, 4. Yeah, here we are now seeing how basically MIP signals are coming up and forming in. So we have this inspect tool, and now you can here see how such a MIC trace sort of looks like.